Today's lesson is on solving linear programming problems graphically. So many mathematical models in business, biology, and economics involve finding a maximum or minimum value, or what we call an optimum value. We can use linear programming graphically to find the solution to these optimum problems. In linear programming, we have two types of equations. You're going to have constraints or restrictions. These are usually going to be inequalities. This is like restrictions on time or resources or anything within your word problem that restricts you somehow. Here are some examples. X plus y is less than or equal to 10. Y is less than or equal to 1/2 x plus 8. Or x is greater than or equal to 0. The next type of equation is the objective function, which is the function that we would like to maximize or minimize. So this would be like if you're trying to maximize profits or minimize costs. So these are things that we often use in economics. So here's some examples. So z is the thing we're trying to maximize or minimize. Z is equal to, and then a function in terms of x and y, 3x plus 5y. With respect to the same constraints you had in the first types of equations. So the second one is z equals 1.5x minus 0.5y. So depending on what your x and y is, we're going to try to maximize or minimize some function, often cost or profits, so that we can find the greatest or least value. So the next thing we're going to do is talk about the steps to solve a linear programming problem. Step 1, write the objective function and all necessary constraints. So for word problems, you're going to be reading the word problem and writing your own functions and necessary constraints. I think today we're mostly going to give you the objective function and all the necessary constraints, and you're just going to have to do the next steps. But step 2 says graph all constraints and identify the side to shade. So just like in some of the previous work we've done, we had to shade multiple inequalities on the same graph. Next, you're going to determine and shade the feasible region. Step 4, identify all corner points which are located at the intersections of the constraints. Evaluate the objective function at the corner points. Now, if the region is bounded, the solution is given by the corner point that produces the optimum value of the objective function. For example, if the maximum equals the largest value and the minimum would equal the smallest value of the output of the objective function. Now, if the region is unbounded, you may not have an optimum value, but if one exists, then it will occur at the corner points. So here's an example for you. So the first one is a bounded region, and we're trying to find the optimum value. So this is already graphed for us. So step 1 and 2 and 3 are all done. What we're trying to do now is step 4, identify all the corner points. So I see a corner point right here at 0, 0. I see a corner point right over there. That's 1, 2, 3, 4, 5, 6, 0. Another corner point right here, which is 1, 2, 3, 4, 1, 2, 3, 4. And then our last corner point, which is at 1, 5. And it doesn't really matter what order you list these in. You just need to have all of the corner points. So step 5 says evaluate the maximum or minimum function at those corner points. So I am going to use my x, y and plug it in. So I have z equals 3 times, I'm going to use the first one, 0, plus 5 times 0, and that gets me 0. The next one, z equals 3 times x, but x is now 6, plus 5 times y, which is still 0, so that's 18. Z equals 3 times 4 plus 5 times 4. So 3 times 4 is 12, 5 times 4 is 20, and 20 plus 12 is 32. And then the last one, 3 times 1 plus 5 times 5. 5 times 5 is 25, 3 times 1 is 3, and 3 plus 25 is 28. So all of these outputs of my optimizing function are going to identify if I have a maximum or minimum. In this particular problem, I have a max at 32, a max of 32. Where did it occur? It occurred at the point 4, 4. So when I'm trying to identify the maximum, I'm going to write the max is 32, and it occurred at 4, 4. Now I'm going to look for the minimum. What is the lowest value here? Well, the lowest value is 0, and where did that occur? At the point 0, 0. So minimum of 0, and it occurred at 0, 0. And that's how you're going to find the minimum or maximum of your optimum function. Let's try this again. For our next problem, again, it's bounded. So I have 4 points again, and this one happens to have corner points at 4, 0, 7, 4, 2, 1, 2, 3, 4, 5, 6, 2, 6, and then the last one is 0, 4. Again, it doesn't really matter the order in which you list out your corner points, as long as you just get all of them. My maximizing function this time is z equals x plus 4y. So I have z equals x, which I'm going to substitute 4 in, plus 4 times 0, and that's just 4. The next one, z equals x, which is 7, plus 4 times y, which is 4. So that's 16 plus 7, which is 23. The next one I have z equals x, which is 2, plus 4 times 6, which is the y. So 4 times 6 is 24, and 24 plus 2 is 26. And my last point, I have x, which is 0, plus 4 times 4, which is my y. 4 times 4 is 16, and 16 plus 0 is 16. So looking for the maximum this time, the maximum looks like 26, and that occurred at the point 4, 6. So let's go ahead and write that in my line. I have a maximum of 26, and that happened at 4, 6. And then my minimum happened at 4, my value of 4, and that occurred at 4, 0. So I have a minimum of 4, which is the output, and it occurred at the point 4, 0. Now, often we're not going to ask you to get both the minimum or the maximum, especially for word problems, but we're just trying to get you to identify which one's a min and which one's a max. But for word problems, usually you're trying to either minimize the cost or maximize your profit. You don't really want to maximize your cost. That wouldn't be helpful to your business, and you wouldn't want to minimize your profit. So, but for these problems, we're going to have you practice both. All right, so this one is a unbounded. I know this kind of looks crazy, but I'm just trying to make sure you understood that this area keeps going on and on and on. So this is unbounded. Keeps going in this direction and in that direction, okay? That's what that means. All right, so I have 2 points. I have 2 corner points, one at 4, 0, and another one at 0, 4. So right now, I'm only going to plug in the corner points, but then we have to really evaluate or think if this is going to have a min or a max at all. So I'm plugging in my values. On the first one, I have 2 times 4, which is 8, plus 0, which is just 8. On the second one, I have 2 times 0, which is 0, plus 6 times 4, which is 24. Okay, so if these were the only 2 points that we considered, I can see a max and a min, but because it's unbounded, we have to really think if this even has a max or even has a min. So what I'm going to do is I'm going to pick another point, okay? So I've already picked my corner points, but I want to see, can I get something even higher than 24? Well, at 0, 4, I was at 24, so what if I pick something even higher than it? What if I pick 0, 6, which is not a corner point, but let's just find out what happens. Is it going to get bigger than 24? Is it going to get smaller than 8? I don't know. So we have 2 times 0 plus 6 times 6. That already is 36. This is already bigger. And it was just a random point that I picked, right? So this is already bigger. So what that tells me is that I'm not going to have a max, because I can keep picking points bigger and bigger and bigger and bigger. If we have a max or if we have a min, it would have been at either 8 or 24. So I can tell you right now we have no maximum. Okay? Just because we were able to find one non-corner point bigger than the 24, I know it's just going to keep getting bigger. And if you think about it, if you keep going out in this direction, you're going to get more and more and more bigger values. So if you want to try one more, we can try something around here at like 5,5. If we try 5, 5, we're probably going to get something again bigger than 24. So we have z equals 2 times 5 plus 6 times 5. And that's already 40, so that's already bigger. So the question now is, do we have a min? Is there any value that's going to get smaller than 8? Well, if I pick a value really close to the smallest, which was 4, 0, let's do 3, 1. If I plug in 3, 1, I have z equals 2 times 3, which is 6, plus 6 times 1. That's 6 plus 6 is already 12. I am pretty sure that my minimum is correct in saying that it's happening at a corner point and it happens at 4, 0. Remember, the minimums and maximums can only happen at the corner points. So I do have a minimum of 8 and it occurs at 4, 0. No maximum because it's unbounded and it keeps getting bigger and bigger as you keep going out.